All right, welcome to week 10 CIV3SD1. Almost there. I think one more topic to go. Stiffness matter next week, and we're done with the subjects. So we're almost there, all long way through. Sorry about that, 4 minutes late. I just came from the graduation ceremony. I like to support the students who have done hard work like you and not going on the last day would be disappointed. It's good to see the students are graduating. Probably, hopefully, after 1.5 years or something like that, you will be graduated. So now, yeah, last week few questions comes and I'm not able to figure it out what is happening there. So let me share the screen for the students online and what is happening. Yep, let's share the screen. All right, now last week there is a questions that we are struggling to answer it. What was that? Let me find that details. Look like there is a geotech lab is working. So a few students did not show up. Anyway, so do you remember this one last week, right? That we have fixed supports because these fixed end moments are also part of this moment distribution method. You remember last week said, okay, you have fixed support 60 kilonewton coming here, 2 meters here, 2 meters here. We have equation in our tables that we blindly follow. No one knows where this direction coming from, what this value coming from, and it was not pleasant to just blindly use it, right? Because we don't know the behind story. So I just did some work on that one. Let's go back again. Okay, so that's the question is if I have a fixed support at A, fixed support at B, 60 kilonewton coming in the middle, what would be the moment and direction? That's the questions, right? That is the fixed and moments. And we have table. We have tables that is you can find it in the lecture notes, and they have given you direction, equation, and you just take it and substitute value, and everyone happy. But that was not the happy end because it was not making sense. So we use force method here. You know the force methods that we teach that we'll use to find the reaction forces in indeterminate structure. This is indeterminate structures. You can't solve with the equilibrium equation. So what we done, let's say degree of indeterminacy, you know the story. 6 take away 3, then axial forces are not there. 4 take away 2, your degree of indeterminacy is 2, right? The structure is indeterminate by degree of indeterminacy 2. Then we say, okay, we change it to the spin support, roller supports, and there was rotations, right? You remember that, right? You make it too redundant. You draw primary structure. Primary structures are determinant structures, and then you find theta A and theta B. Theta B, theta A. Look, the direction that I have here, I don't know the direction initially, okay? By the way, this one I just put it randomly. You can put it randomly, we don't know. So if we get negative answer, we change it. You know the story, right? So don't worry about that direction, I just assume. Okay, based on that assumptions, we get this theta A negative because you can see this theta A going clockwise negative, anti-clockwise positive, theta A and theta B. And that's the equation to calculate the theta A and theta B. Okay. Now you might say where this coming from. I think you can do the virtual work method, and there is also 2-3 pages of work. Okay, if you want to, you know how to find the displacement and rotation now by virtual work method. You can put the virtual moment and then blah blah blah. You know that. So you find theta and theta B from your primary structures. Then you say, okay, you apply unit moment and you find the FAA, which is flexibility coefficient. You know that, right? When you apply 1, then you find FAA, which is opposite, by the way, to that theta A, and you find that FAA, FBA for this one. Then you do same numbers for 1 here, and you find FAB and FBB. Don't worry if it doesn't make sense too much to you, but that is just overall procedure. Then we use compatibility equations here, and then we find we find theta A, and we find this, this from the compatibility equations, we can able to find these MA and MB. Like this, if you can first find theta A, and then from that theta A you can find MA and MB. That is just the procedures that, and from that MA and MB you can find this one. What I found, they are both positive. MA and MB, you can see this 30 should goes, this 30 just written here. So I found that MA and MB equal to 30, 30, meaning that my direction, which I assume is correct. Now again the questions come, so this is good. Now the questions get complicated here. Complicated here meaning, I think this one is not complicated, meaning that if you have a structures like this, and if you have a 50 kilonewton meters, then I keep it the same directions. Right? There's another question comes saying that instead of 60 kilonewtons, let's say what about 50 kilonewtons meters moment, and then this direction goes this way or this way, in equilibrium and so on. There was a question. So in that case, we do again. We draw primary structures, 50 kilonewtons. This is your deflection curve. Because of 50 kilonewton, you find theta A, you find theta B. Then you apply the unit moment, you find FFA, FBA. Then you apply unit moment here, you again find FFA, FBB. And you do compatibility and look at here the answers. The answers would be this negative. One is negative. What does it mean? That my assumed direction, which is this way, it was not right. So I need to change this one to this way, which is 12.5, and this one would be 12.5. So that's what in the tables, you remember that, right? Everyone remember that question, right? That we have this, why this one going this way, this one coming here, why going this way? There is a whole story.
So we have to remember that for the exams and stuff, or would that be?
So you have it in table. You have a table that will given to you in the exam. This table. This table. This table will be with you in the exam. But the questions coming, I don't want to just follow blindly where this coming from, where this coming from. That's what the questions come last week, right? Saying how why this one going this way, why not this way, why this one coming this way, why not this way. That's what the questions. So we can derive that using the force method. It's just a reaction. It's basically the reaction force is due to the loading. That's what it is. Okay. All right. So that's the last week one. Now we're going to work on the friction moments. Let me week 10 workshop, and let's oh, by the way, before we start, I think we need to do the student feedback survey. That's I almost forget. Can you please fill out this student feedback survey? I'll give you 5 minutes. This one, if you go to your LMS page now, and if you can just spend 2 minutes for me, it will be anonymous. I don't know who put what. And if you just give me your feedback on the subject teaching, that will help me to improve the subjects. Then what's for you? Yeah, that's a good question, right? I'm teaching SD2 and SD3 next semester and following next year. If you give me your feedback, what is working, what is not working, I can improve the subjects. One student asked me in the past saying, my salary gonna increase? If I fill out this one, my salary will not increase, my salary will stay as it is. Just this is for me to see whether it's working or not. You see what I mean? Because I don't know, I'm just teaching, and I don't know which one is working and which one is not working. So I just want to see what is feel like when you are sitting there and what attending. So it's completely anonymous. I don't know who put what. and I'm not sure whether you fill out or not. So I just give you 5 minutes. If you like, just go over here and just put your feedback. You know, if you go on your LMS, my subjects, and you can find maybe this kind of button on the right side, your evolution, and then just fill out that for 5 minutes if you can. Did you find it, anyone? You fill out, Rana? You asked me a lot of questions, so you must fill out. Don't worry. While you're filling it out, I prepare my example. This is all good now. We're going to use the Excel as well. Probably this example in the workshop would not be good enough. So we will take the example from our lecture notes to see if we can get Excel. All right, so I hope you fill it out, and thank you for filling out those. To give a comment. Now, the question is determining the moment at the support A. We need to find the reaction moment. At B, we need to find the reactions, vertical reaction here of the beam with a stiffness EI. So you have 2 EI, 4 EI. For each span, indicate in the figure, draw the shear force diagram and bending moment diagram. Okay, so this is the indeterminate structures. What is the static degree of indeterminacy? Static degree of indeterminacy, force methods. No? How many reaction force here? 3. How many here? How many here? How many total? 5. How many equilibrium equations? 3. 5 take away 3 equal to 2 static equilibrium, which is used in the force matrix. Just to give you an review. Now, kinematic degree of indeterminacy. 1, yes, that is here theta b. We generally take it 2 because we have theta c as well, because it's not a fixed support. But we don't take into account theta c because we know the moment here is 0. There is no any end moment, so we don't need to solve theta c, by the way. So that kinematic degree of indeterminacy we don't need to take into account. You understand? If someone asks you just a pure question, what is kinematic degree of indeterminacy? We say 2 as a first. But when we start solving it, we just reduce our work by saying that because when you have 2 kinematic degree of indeterminacy, meaning you have 2 unknown and you need to solve. But because the 2 unknowns will going to give us the end moments, but because we know the end moments here, which is 0, this is the roller support, so we don't need to find the end moments here. So for that theta c, we say we don't need to worry about, right? Because it will just not going to helpful on our calculation. So in that case, we have kinematic degree of indeterminacy equal to 1, which is theta b. Theta a equal to 0. Theta b is unknown. This is a fixed end moment tables that we're going to use it for your reference. That is in our slope deflection methods, and that's the stiffness one. So how do we start? The start point is what we do. We make all the internal support fixed. You know that, right? So there are a couple of steps that we follow. If you know from the lectures from the from yesterday, that how do we solve? First, we're going to find the stiffness. What is stiffness? Yesterday, I talked with in the lectures that students said I did not heard about stiffness, but I think in the lectures we introduced something stiffness. What's if someone say that 10 Newton per meter stiffness and someone says that 5 Newton per meter stiffness for the beam? Let's say I have a beam here. This beam is 5 Newton per meter stiff. This beam is, let's say, 10 Newton per meter stiff. What does it tell you? You know what I mean? So what is stiffness? Hard to bend. Yes. So stiffness, how stiff it is, right? So if I take a spring and then if I load it with some force, then this displacement stiffness would be P over delta. That is represented by capital K. That is the stiffness, load, displacement. The more the stiff, it's very hard to displace. Okay. So stiffness, we have 2 equations. One is this one, K is equal to 4 EI on L, and another one is K equal to 3 EI on L. When the both supports are fixed or far end is fixed, this is far end, this is near end. When far end is fixed, we need to use that equations. When your far end is roller or pin, then you use these equations. Okay, this is far end and this is near end, right? All right, so now in our examples, if I have a AB where B is a fixed because it's the internal supports, I can use this first one, that KAB is equal to 4 EI on L AB. 4 EI value is how much? 2 EI. So let's plug it. 2 EI. Length of AB is 4 meters. So this cancels. We have 2 EI, the stiffness of KAB. Now KBC. Now in KBC, this C far end is roller. So in that case, we can use the second equations, which is 3EI on LBC. 3 EI is 4EI on length of BC would be 4 meters. So 3 EI. Look at the stiffness. 2 EI for AB, 3 EI is AB. Remember that AB 3. So which one is more stronger, AB or BC? BC, right? So if I have a, let's say you want to design the platform. Let's say you are an engineer and you got the job in Tesla in US and say that, Elon Musk said, okay, you are structural engineer from Laptop University. I have a 10 Tesla and I have 5 Tesla. And you have 2 beams. Where do I park 10 Tesla and where do I park 5 Tesla? So you quickly go and do the stiffness equation and say that, here you can park Tesla because there is this beam is strong. It will not going to deflect. Okay, that's the stiffness on. And let's look at that. Stiffness is depend on your EI value and depend on the length. Length is same. Your EI is higher, so that of course this will be more stronger. Okay. So it's just, you don't need to just blindly follow. You just need to feel that what is happening. So stiffness, everyone okay? Yes, please go ahead. Is 4 EI, and then later on, if they change it or they will continue working on 4 EI. That's what you saw. Okay, let's keep rolling. You're smart enough, so that's. I will do that. Okay, that's okay. All right. So we will keep rolling and see if they change it back to 3i or not. Yeah, so that is just a typo. Yeah, that's good. All right, no problem. Now, second one, we find the distribution factor. Now, let me get this beam here. Otherwise, we will continue keep going up and down. So let me get this. So member AB, distribution factor of AB. A is fixed. What is the distribution factors for A or distribution factor AB? Fixed support. Why 0? No, it's not like that. It says and you need to read it. Why? When you have a fixed support. Yeah, it's a very rigid. So what is the equation? Look, what is the equation for distribution factors? Is the stiffness of the member where you want to find over the total stiffness at the joint. Right? That's the definition of the distribution factors. That you want to find the distribution factor of AB divided by the total distribution at that particular joint. Now, distribution factor of member AB is KAB, stiffness, divided by joint A, infinity. It's fully rigid, it's strong. Some number divided by infinity is 0. Does it make sense? That's how it's, we just go by definition. So you said 0 because A is fixed. Right? Now, distribution factor of BA equal to KBA over KBA plus KBC. Right? You with me? Because I want to have now joint B, and at joint B you have KBA over KBA plus KBC. Now stiffness of KBA we found here, which is 2EI over 2EI, and KBC is 3EI. So EI cancels 2 on 5. So that will give you 0.4. Distribution factor of 0.4. So what does it mean, distribution factor of 0.4? What does it mean that this guy here, if I take the joint, because this joint will have two members connected, AB and BA. So if we have a moment at B, 40% of moment will go here AB. Do you remember the example of Tesla, 4 cars and all? So this guy AB will not going to take much. If I have a moment here, this guy AB will not going to tell, it's going to take only 0.4, 40% of that moment. This guy gonna take 60%. You can see that from our calculation. So as I mentioned, this one is stronger. So distribution factor of BC equal to KBC on KBA plus KBC is equal to distribution factor of stiffness of KBC. We have 3 EI on 2 EI plus 5 EI, and then you have EI cancels 3 on 5.6. I stop here and I request you to check. At joint B, you have 0.4 and 0.61 always. At joint number B, your distribution factor always add up 1. If it does not add up, go back and check the calculation. Okay, this is your key checkup for you, that how this distribution factor must add up 1 at that particular joint. All right. Now distribution factor at CB equal to KCB over this KCB plus roller. There is no stiffness. This joint B is a roller. So roller is not stiff. It does not resist anything. Therefore 0. So KCB over KCB equal to 1. Same stiffness divided by same stiffness 1. So the takeaway message: fixed support, 0 distribution factors, roller or pin, you have a distribution factor 1. Any internal supports, you do the calculations and you must check that all the internal supports will add up 1 distribution factors. Any question in finding the stiffness distribution factors? All good. All right, let's continue. Now the next third steps, we're going to do the fixed end moments. I think you done the fixed end moments previously. Let's get this figure back to here. Here, and let's get this table down. All right, now all the internal supports are fixed. Okay, all the internal supports will be fixed. So fixed end moments at AB equal to, because if I draw the AB, I would get 60 kilonewton here, 2 meters and 2 meters, which is 4 meters here. And this will be fixed end moments of AB. And this is fixed end moments of BA, because this is A and B. Right, so clockwise is positive. So this is anti-clockwise. What would be the equations? PL on 8 minus 60 kilonewtons, length 4 meters over 8 would give me minus 30 kilonewton meters. Right, and then similarly, fixed end moments of BA, which is clockwise, which is PL on 8, 60 times 4 meters on 8, which is positive 30 kilonewton meters. Right? So we find friction moments, and we find due to this 60 kilonewtons. Second one, B, and the roller pin, we can't touch it, that's C, and we have UDL load of 20 kilonewton per meters with the friction moments of BC. So where is the similar figure here? WL square over 8. So friction moments of BC minus W, because it's anti-clockwise, minus 20 kilonewton per meters. Length is 4 meters. 4 meters square over 8. It gives me minus 40 kilonewton meters. And you know the direction and all sort of things, right? If you don't know, you do force methods, and you can just assume that you don't know this one. Reaction you will find 24 roller supports, and you do all the procedures to find the reaction force, and that is the that's I just give you in the first of when we start the lectures. Now the difference between this method and slope deflection method, they are both part of the displacement method. This moment distribution method and slope deflection methods both are part of this one. On the previous slope deflection method, we used to find theta A, theta B, we plug back and we find the moment and moments. In moment distribution method, it's a very powerful method that will bypass that theta calculations, and it will straight away give you the n moments. 1930, Professor Hardy Cross found these methods. Up to 1980, all the buildings was designed using these ones. And the stiffness method step in 1980. Computers start using. So after 1980s, we start using computers for the structural analysis. That next week we will tell you how to solve that using the computers. So now we need to build the tables. Now here you will not get exact in these examples. You will get exact solutions because I know this example. But you remember yesterday lectures, it was not exact. There was an error which we ignored, less than 1% error. You remember that? So it's not exact solution. Slope deflection meters give you exact solutions, but these methods will not give you exact solutions, right? It's very minor errors that you are end up with all the time. So how you build the tables? Let's write the okay. Let's bring that figures down so we know what we are talking about. All right, here is the figure. All right, so let's do this. Now the thing is, we have joints. Always start with joints. How many joints? A, B, and C. If you are working in your notebooks, can I borrow it? If you start with the papers, always start with the start of the papers. If you start here, you end up with running out of space. You need to transfer it here in the exams too. Okay. So when you start the tables, always start with your new paper. If you are working in these smart devices, you don't need to worry about it. But in the exams, you might not have this smart device. Then you need to start with your on the top of the page. You might need some space there. Right. Now, so you always start with joints. Then from the joints, you draw the line, vertical line. From the joints, draw the vertical lines. Then next one, we write members. AB from the, what is the right side? AB, then BA, BC, and CB. I hope you don't have any issue to write those names. You have joint A, AB, AB. Joint B, BA, BA. Joint B, BC, BC. and joint C, CB. Right? Look at the figures and you can frame it. Next. You write distribution factors. After distribution factors, we need to draw a line, I think, yep. After distribution factors, draw the horizontal line. Right, we can just go back on our previous calculations and somewhere we said distribution factor of AB is 0, BA is 0.4. AB is 0, just put it in the square. BA is 0.4, 0.6, and 1. When you write those, keep in mind, joint B, make sure when you copy it down, sometimes I also make mistakes that I might copy 0.4 or something different. You know, I misread it. So make sure when you write it, make sure it will add 1. Make sure it is 0 when it's fixed support. Make sure it is pin or rollers when it's 1. So just be active what you are writing. Okay, it's just not blindly copy from the previous. You might end up with this one. Just have a feeling what is happening throughout the examples. Okay. Now that's done. Then the next step, we're going to write fixed end moments. And for fixed end moments at AB, I think we done here minus 30, BA positive 30. Minus 30, positive 30, and BC minus 40. We don't need to write unit. And let's say for completeness, we just put the 0. Dummy 0, okay? There is no fixed end moments here. CB, we just put 0 for our mathematical calculation. So far, so good. Any questions? Right? It's just a simple process. If you do it a couple of times, you will get it, okay? It's not so difficult. Fixed end moments done. Then we do balance 1. What is balance? The balance is, look at here. Look at these fixed end moments. 30 take away 40 minus 10 extra moment at joint B. Do you agree with me? Because look at the joint B. We always start with internal streams. Look at the joint B only. You have 30, which is positive, which is going clockwise. You have 40 minus 40, which is anti-clockwise minus 40. If I add them together, I have extra minus 10 kilonewton meters, which I don't want because you look at the original figure. There is no any moment. There is 0 moment. But in my calculation, there is an extra minus 10. Do you understand? That is called unbalanced moment. That is the moment distribution method. Name is moment distribution method. So we need to distribute unbalanced moment, continue the process until we get very small balanced moments. Okay. So I have extra negative 10 kilonewtons. To make it negative 10 to 0, I need positive 10. I have positive 10. Then I have positive 10 here. But this guy AB is telling me that I can take only 0.4. I can take 40% only. I can't take more than 40%. Do you understand from distribution factors? That is written here. That if you have extra moment, I can take only 10 times 0.4. I can take positive 4. Okay, so I can write here. How does it come in mathematically? So 30 take away 40, give me minus 10. Then you change it to the positive 10 to make it 0. And times by distribution factor 0.4, it's give me 4. And here again positive 10 times by 0.6, it gives me 6. Now if you sum them all four, 30 minus 40 plus 4 plus 6, you will give a 0. Right? So that is called balance. We continue this process over and over again until we get the very small error. And I will tell you how to find those errors. Now, in the old days, 1950s and 1940s, they stopped it at two interactions. Two interactions means first one and second one. That's it. And they said, we have errors, but we live with errors, no problems. Okay. So, but now we have Excel and all. We can use, and no one use. By the way, no one use these methods nowadays industry. And you might ask, why do you teach us if no one's using it? Well, that is very famous that we need to learn the history to not repeat the history. If you don't know history, you might saying, oh, that is new. Let me do it, but it's already done. So no one's using it, but it's very fundamentals, and therefore we still teach it. There is a foundation of those displacement methods. So balance one, I think, by the way, you need to write just a little bit 4 and 6, little bit down here. 4 and 6 in front of that. And this one minus 30 times 0, 0, 0 times 1 is 0. Okay. And then after balance one, you need to draw the line and say that carry over 1. And then carry over from here to here is carry over factor is 0.5 or 0. What is happening carry over? If I have a fix here, I hold it fixed. And if I apply, let's say 10 kilonewton meters moment here, then it will become half here when it's fixed. When you have pin and rollers, it becomes 0 because I let it go. So the carry over from B to A, is 0.5 because whatever the moment here, it will become half here. And carry over from A to B is 0.5 because you have B is fixed. Carry over from B to C is 0 because this is a roller. From C to B is 0.5. Right? So carry over from here is 2, 0.0. So it's just multiplying by 0.5. Carry over from here 0 because it's multiplied by 0. It is roller, and that is 0. Okay, and then you never stop at carry over. You always end up with the balance. Okay, you not stop that one at the carryover, and you write balance. Balance 2. And then you will have 0, 0, 0, 0. If you are lucky, you will get all 0, and then you can stop.
Scroll up a little bit.
Yes.
I just want to see that.
Yeah, carry over. You can check. If I have moment at B, how much moment gonna go at A if the A is fixed? If I have 10, it goes 5. If I have 4, become 2. If I have 3, become 1.5. If I have moment at A, B is internal fixed. How much moment gonna carry over? If I have 10 here, it will become 5, 4, become 2.
So that point B is technically fixed. Is that what it's saying?
All internal supports are fixed. We clamp it at the start.
Yeah.
And we don't touch the end supports. All right. So we done this one. Finish it up. Sum the moment. Minus 30 plus 2 minus 28. 30 plus 4, 34. Minus 34 and 0. What I done? Minus 30 plus 0 plus 2 plus 0 minus 28. 30 plus 4 plus 0 plus 0 plus 0 34. Minus 24 6 0 0 minus 34 all 0. I stop here and make a check. My table is correct or not. They give me the hint here. And if this number is not same and opposite, then you might end up with a different one. Yes. Yes.
I've got a couple of students who want to use the computers in here. Is it okay if they sit in the corner? They're not going to disturb.
Yeah, don't make noise, then okay. All right, so this 34 and minus 34. You got it? So if you screwed up something, carry over is not there, balance is not there, you do plus and minus, you know, you might you might end up with some different numbers. Then you end up with different numbers, and you know that there is something wrong. Go back and check. Okay. Now we use Excel for your assignments or for to do the checks. Okay. I will show you how to use the Excel and how to build it in the Excel. Okay. It's very easy. Students may ask, can I copy it from the Excels? Please don't do it, because in your exams you don't have Excel. This Excel is just for you to make a check when you do the long calculations. All right. So if everyone wants to work with me, please open the Excel. All right. In the Excels, we're just going to follow exactly the same thing that we have it here. Let me copy it here. All right. What we do, first we'll write, say, don't worry about the joints. We'll start with members. Let's write members. We have member AB. Just look at here, member AB. Then we have one gap. So leave one gap, and let's say member BA and member BC, and there is a gap. Let's leave one gap, and let's write CB. And let's put it this one in the center. It looks neat. If you don't leave gap, that's okay. It's up to you. Yeah, that looks squashy a little bit. But that's okay. If you don't want to leave gap, don't leave a gap. All right. So once you put those members, you can write next one is distribution factors. Let's write distribution factors DF, and that will have a 0, 0.4, 0.6, and 1. And let's put this one in the color, because we're going to use them like we need this value for every step. So let's put it that in the highlighted. They are very important for us. Right. Now, after that, just look at our figures, okay? Nothing new we are doing. We have after distribution factors, we have line. So let's draw the line. Let's draw the line here. Let's put the line here as well. Vertical line here. And we draw the line after distribution factors. And then we say fixed end moment. Fixed end moment is minus 30 and positive 30 and minus 40 and 0. Right? And then we do balance 1. How do we do it? Equal to minus type sum open bracket, select these two that you want to sum, bracket over, times by these distribution factors. When you times it, select this one both two and press F4 in your keyboard. If you can't, then you just type the $sign in front of them to lock them up. I think there is a minus sign here, not before. And enter 4. Look at your figures. You have 4 there. Same thing here, equal to minus sum. Select these two times by distribution factors. Select these two and press F4, or you type the $sign. 6. Yep, everyone okay? You all got it? -1. You put minus in front of that. Yeah. Yeah, that's good. And the same thing for next one. Yeah. So 4 and 6. You made a colorful, which is good. You need the Excel skills. All right, 4 and 6. And then same thing here. Equal to minus sum. This one times by this distribution factor, log them up using this tool. Minus sum, these numbers times by distribution factors, $sign, and that's it. Balance 1. All right, after doing balance 1, we draw the line, I believe. Yep, we draw the line. We draw the horizontal line after balance 1. Right. Then we do carry over 1. If you can't fit it, just put your cursor here and double click it. It will just automatically expand the columns. Now the carry over, you put equal to sign in the first one at the B. Select this 4. And I think you have 0.5 here carry over. So times by 0.5. Select this cell 4.1 times by 0.5. Press enter. Same thing here, equal to, press this one. I think here you have a carry over 0.5. Enter. You just do once and you just copy this one. Control C, Control V. But I think we have something different here, because here you need to put I think don't worry about it, because here we have a different one. So just delete that. So you do equal to this one times 0.5, but this one times 0. That's what we done, right? So this one, first one across 0.5. Second one across 0.5. This one across 0.5. This one across times by 0. Right, you done once only, and then the magic happens in the Excel. Yeah, we need to balance, but Why don't we take the advantage of we already done the balance? That's the computer. We done once and we repeating. So the Excel can repeat for us. That what you do, you select these two, balance and carry over. This first one you done once, and because the rest is the repetitions that you done one, then you can find this little, you come here, there is the little triangles, you just hop over here and you can see plus sign. Once done in the plus sign, and then you drag it, and that will do it the job for you. It can do it hundreds for you in a second. Right? That's what we got it, right? Is it the same? 200. Yep, 200 and after 00. But we always stop at the balance. So just let's make it one more balance, okay? And then we sum all the moments. How do we sum? Equal to sum, bracket, select all the one from here to here, enter. Equal to sum moments, here 34. Equal to sum the moments, here minus 34, and equal to sum that's what your hand calculation should give you. Now this example does not give us a lot of advantage for Excel. So what I suggest, I think we done in the lecture, but I think I quickly do it for you. What I suggest, let's do this one by Excel in 5 minutes, okay? Because these first examples in this one, it will not give you a lot of advantage. So if you want to practice one more with me, we can do these examples. That is in our lectures. I think we done it yesterday, but if you want to practice here with me, we can one more practice and then we can go on that next examples. Because this one don't give you too much advantage. So let's do the same thing. Let me copy this one. Let me go one more sheet here and put it here. All right, first thing first, you write members. You have member AB, leave the gap, member BA, member BC, leave the gap, CB, CD, and leave the gap, and DC. Then you write distribution factors, 0, 0.5, 0.5, 0.4, 0.6, and 0. And put these distribution factors and I think after distribution factors, we draw a line. You can refer our last examples in this sheet. If you don't remember distribution factors, I encourage you to save this Excel file with you and leave it with you. If you forget how to do it, you have a copy in your systems. Save this one, use it in your USB or somewhere, keep it storage. So if you want to refer back, you can go and check it. distribution factors done, then you do the fixed and moments. Moments, first one is 0, BA is 0, minus 240, 240, minus 250, and 250. You can stop me if you are not following, or if you have any questions. Don't hesitate to ask questions if you think that something is not working. All right, once you've done the fixed and moments, sit. All right, so balance one. I think you come back here, you say sum, and you select these two, bracket over, times by distribution factors, and press F4, or you can just fix up here. It's 120 minus sign sum times by distribution factors, log them up at 120, 120. Here equal minus sum, these two times by these distribution factors. We need to log because we're going to multiply these many times, and equal to minus sum times by distribution factors, and equal to minus sum this distribution factors. We like to log this, and equal to minus sum distribution factor and then after balance, I think we draw the line. So let's put this line here. And then we do carry over. You just come here and just expand. And the carryover would be this times 0.5. Because these are all fixed supports, we can do the copy paste. This times 0.5. So we will just take this one, Control C, Control V, Control V. Make sure when you do it, make sure it's picking the correct value. Just click on this one and make sure it just pick up the correct values. Just the last time we done it, exactly the same. And you do once. You do once meaning once you done this one, you just drag it until you get smaller numbers. how much smalls you gonna get? You need to check the errors. You just need to drag it. Oh, sorry. Just drag it. Yep. How much you going to do it? I think you just need to check the error. How do you going to check the error? You can sum this one up. I think the carryover that here, you need to sum this carryover. So let's say equal to sum. This carryover divided by sum these fixed end moments times by 100. Yep, is less than 1. It's pretty much good. You need to check it here as well. Is equal to sum. This one divided by sum. Oops, sorry. 100 for the percentage. Both are less than 1%. We can stop. Okay, so you can do it, and then finally you need to do this sum. Equal to sum. And that's your up to fixed end moments. That's your final answers. Is equal to sum. Is equal to sum. Is equal to sum. All right, so you can do this one. If you done the hand calculation for your assignments, you do this one to verify your work. Do not please do not do this one first and copy paste there. It will just stop your learnings. So that's the overall message. Ask me if you have any questions. The next one is just going to be repetitions. All good then. Let's move on to the next questions. Next question is here. All right. All right, so what's it's not showing, not changing. Yeah, back, but All right, small technical issue. Now, what we need to do is determining the moment at the support B and C of the beam, so on in the figure. Then calculate a reaction at the support and draw SFP and BMD and assume the support A, B and C are roller, B and C and A is spin. So the figures look like here that A is spin, B is roller, C is roller. Let's remove this overhang part. And instead of overhang, I can write 1200 newtons times by these 2 meters. So 2400 Newton meters. UDL load, Newton per meters, 2.5 meters. And that's it, right? Then same styles. Stiffness, 2 equations. Stiffness of AB, 3 EI on L. 3 EI is same, length is 2.5. So 3 on 2.5, we get 1.2 EI. Stiffness of BC equal to the far end is spin or rollers, 3 EI, and this is 2.5 meters, 2.5, 1.2 EI. Both are equally strong. Right? Same length, same EI, stiffness is same. All right. Now distribution factors for AB. A is spin, so distribution factor is 1 because A is spin support. Distribution factor for BA, KBA on KBA plus KBC, 1.2 EI on 1.2 EI plus 1.2 EI, 1.2 on 2.4, 0.5. Distribution factor for BC, KBC on KBA plus KBC is equal to, I hope it is not too fast because we done this one. I can stop here. We done the stiffness first. And now we are working on distribution factors. And we done AB, BA, BC, and CB. Because C is roller, right? So this is all pin roller. Distribution factor is 1. Internal supports, distribution factor should add up 1, and the fixed support distribution factor is 0. Right? Stiffness, 2 equation, 4 EI over L, 3 EI over L, and 3 EI used when you have a roller or pin, 4 EI when your far end is fixed. Raise your hand if you are not in the positions to apply the stiffness equations and distribution equation. I can go in details. Once the distribution factor done, we have a tables to use the fixed end moments. Fixed end moments of AB equal to, I think internal supports are fixed. So we have a internal support fixed. This one is spin. And that is A, B. And then we have fixed end moments of fixed end moments of BA. I think BA AB is 0. Fixed end moments of BA equal to clockwise WL square on 8. You can look at the this is 3200 and the length is 2.5 meters. 2.5 square over 8. You get fixed end moment of 2500 Newton meters. We have a table. Look at the table. In that tables, you can find phi P. B is internal supports fixed. We don't touch the end supports. Okay, so we find the fixed end moments. And you know why we find the fixed end moments, right? Because displacement method does not like the load coming onto these members. It likes when those loads the moments at the joints, and then we distribute those joints, distribute those moments. Right. After this, we build the tables.
Then we need one for fixed end moments from A.
Fixed end moment for B to C. Let me explain it. B, C, 24 Newton millimeters. Oh, yep.
Yeah.
What was my questions? When you have internal load, displacement method does not like it.
So it doesn't like it exactly on the beam, but it doesn't mind if it's on the joint.
I told you, we need the joints. What we done here, this is on the joint. This is on the joint. This is on the joint. So here we see displacement matters. This is what I want.
Okay.
And you give me that one. So you don't need to worry about it. Here it says, you are putting the load on the beam. I don't like it. What you need to do it, that I need the equivalent load that should be sitting in the joints. So the displacement method is work like this always. So what scenario we have right now? We have first scenario is this one. 2.5 meters, 2.5 meters, and we have a UDL load of 3200 Newton per millimeters, and we have 24 Newton millimeters. That is the first. This is the first scenario. Then displacement methods for this to make the displacement method happy. What we done? 2.5 meters, 0.5 meters, 2400 Newton millimeters, and look at the figure first and figure second. To make the displacement methods happy, I removed 3200 Newton per millimeters. Instead of 32, I put 25 Newton millimeters. Now displacement method is very happy here. You don't have any internal loading. You don't have any internal loading. All loadings at the joints. So we first, we say you happy. Now we come up across with problems. The problem is we have unbalanced moment. Just look at this one here below. This joint B is unbalanced because joint B should be some of the moment at joint B should be 0, you know. But there is an extra moment 2500 Newton millimeters. Then joint B is connected by 2 members, so it should be goes. How it goes? Distribution factors. Right? So this is how the problems right now we have. And now we're going to use the tables to distribute. If you don't want to use tables, you want in the figures, you can do it. If you are smart, you just do this, keep writing it. The table is just for to teach, to simplify. It's not the table is not part of the methods. It's just for us to structure it and frame it. All right, now let's draw up the table. As you know, first we write joints. And from the joints, we draw up the line. And then we write members. AB, BA, BC, CB. Then we write distribution factors. distribution factors are 1, 1, and 0.5 and 0.5. Then here we have a joint moments. You can look at the original one, joint moments. That's what we need to start with. When you have a concentric moments, that's your starting point. Okay, so instead of fixed end moments, we write M joint. And that M joint is sitting at CB 2400. There is zero joint moment, zero joint moment, zero joint moment here at the start. And then we do carry over first one. So that would be 0, 0. This will go 0. This will become 1200 because all internal supports are fixed. So joint B is fixed. And then we're going to write the fixed end moments. The fixed end moments are 0, 2500, 0, 0. Right? Because we have a fixed end moment for B at 2500. Now we have unbalanced moments of about 2700. Right? You can look at that one. So to do that one, we need to make it minus 2700. Then minus 2700 times by 0.5. You get 3700 here. So that is 3700 positive. Then we make it minus 3700. And then minus 3700 times by 0.5. It's give you 1850. So you have balance 1 minus 1850 minus 1850 0 0. And then you do carry over 2. This will get 0. This will get 0 because carry over here is 0, 0. We don't stop at carry over. We do one more balance 2, 0 0 0 0. And then we do sum 0, 2500, take away 1850. You get 650, get minus 650, and you get 0. Right? Oh, by the way, this is 2400. We have concentric moment. Any questions? After this, you can do the statics. You know the statics, how to do the statics, right? You put the n moments, or do you want me to show it? Statics. You okay? All? You know, you just take this. You can take this part here, A and B. This goes here. There is a 0 moment here, and clockwise 650 moments. And then you have 3200. 3200 Newton per millimeters, 2.5 meter, reaction 8, reaction B left side. And you do statics, you can find those reaction supports. Right? Once you find the n moments, you are on your way. On your way, meaning that you have done those equilibriums. Right. I think this is just a repetitions, but for the completeness, we have half an hour. If students wants, I can show you the next one, which is the frame one, how to solve the frame one. Everyone who has a request to do the frame one?
I'll watch it later.
Yeah, that's okay.
Yeah.
Any request for frame? No, all good. Rana, the last one.
Yeah.
Yes, okay, let's go. All right. So the frame is not a difference from the what we call the beam. The recipe is same as just a different flavor. Now stiffness first. AB moment and the member frame with the stiffness EI. Each member indicate assume that support A, D, and E are pin. So A, D, all are pin. Okay, so we have this member AB, which is A is pin, and this one is fixed AB. Right? For that case, stiffness KAB is equal to 3 EI over L, and EI is 0.8. Length is 2, so we got 1.2 EI. Stiffness for BD, B is fixed. Oops. D is pin. For that case, KBD is equal to 3 EI on L. So we have 3.6 on the length of this one would be 4. So you get 0.45 EI. Stiffness of KCE. Now let's do the CE. C is fixed. C is fixed 4 meters. E is spin. So 3 EI on L. 3 EI is EI. Length is 4. So you got 0.75 EI. Stiffness of KBC, because both are fixed now. So we can use, so BC is fixed. So 4 EI on L. 4 EI is 0.8 EI. Length is 6 meters, equal to 0.53 EI. Right? Yes, please.
This question I didn't like earlier. No, I just wanted to know how you do the table. Would you just A to B to D? That'd be slightly different since it's
Yeah, because you have a joint B, so joint B has a 3 members. So in the when you draw the line, joint B, you draw one member here, one member here, and one member here. So instead of drawing just one line, you draw 2 lines because there are 3 members under the joint B. And then procedures are same. Balance, carryover, balance, carryover. Others has only 1 member or 2 members. You are dealing with 2 members so far. You have 2 members. You draw when you draw the line. When you have drawn, like in the previous one, you have, let's say, BC and CB or something like that. Here, joint B has a 3 members. All other joints has a 2 or 1 members. Right. So when you have joint has a joint BA, joint BD, and joint BC. Like you have 3 members. Then you write distribution factor for each member. You write the fixed and moment for each member. And you balance it out and you do carryover.
We don't do the carryover for the middle.
No, you do carryover for middle members. No, middle members, because what is happening in the carryover BD. So you just need to think. So if you have a moment at D, how much would be carryover at D? That would be 0 to the D. You can do it this one. You can look at the tables, and then if you have a DB, somewhere here DB, because if you have joint D and you have DB, from BD to DB is 0. Because BD and DB are same. How do you carry over here? Joint B, let's say you have a moment at joint B, right? In that moment, how much moment will gonna go here? That would be the moment in DB. That would be 0 because this is spin. Carry over is 0 here. You see what I mean? So whatever the moment for BD that will be here, that will become 0 in the next line for DB. And for BC, you have a moment BC, and this is fixed. So carry over 0.5. If you go here, that would be 0.5. From C to B, it would be 0.5. From B to A, 0. From A to B, 0.5. So you need to look at the table. Let's say you have moment at BA, look at the figure. BA, where it goes. If you have moment at BA, it will goes to A. And A is spin, so it becomes 0. And that will be AB. Do you understand? Do you want me to show? It's okay. That's okay, because you have only one request. Any students has a request or anything? Because it will be complex and it will be boring and dry. And keep talking for 1.5 hours. I'm happy to do it if it is add the value, but it will not gonna add any value. And believe me, if you look at me for 100 times, it will not gonna make any difference unless you do it particular that assignment questions. Then it will make a difference. All right, any questions? Yes. Yes, been here. Yep. Can you just hop over on this one and say that cost fix and what is this one here? Cost 3 are fixed. Yeah, we use this one. Let's do. Yeah, so what happens here? Let's think this one. What is happening here at joint E? Joint E cannot go in X. You agree with me? Joint E cannot go in the Y. Do you agree with me? That's what this one. And if you allow rotation. Okay, if you go back here and we check it, the notation. So first X fixed, which is cut. Second, Y is fixed, which is this one fixed. Z fixed, right? Rotation is fixed. We don't watch the rotation about X. No, we don't worry about the rotation about X. We don't worry about rotation Z. So I think it'll be fine. Yeah, we just want to see the displacement. Yeah.
Do I input all the links?
Oh, okay. So you click on that one, one member.
Yes, we can do subtotal range.
And then you come back here.
Thank you.
Thank you very much.
See ya.
See you. 1500. Yeah. First, I think first you need to enter. First you enter something. No, first you put universal beam or something. Yeah. Just put any dummy one. Yeah. Then we change that to this one to
make this easier.
1600. Ah, no, this is the polar moment of inertia. Doesn't matter.
I don't have mine here because I was
200,000. You can so to
yeah, so you can that's on the
yes, because you they will put the same one, but now you need to this 1600. This is 1600. So you don't need to make a changes. You make the changes where
this
you want it to.
yeah, from that side.
Yeah.
Because then you won't have that X1.
You need to press OK, I believe. Otherwise, it will not be same. I'm not sure.
Yes.
Then you get
Let's stay. Yeah, that's okay.
you do this one.
That's
1, 2, 2, 5.
Keep on with this one.
Yep.
Keep down here, you have one.
So they change. They change all to these particular things.
You wanna put one at,
So what
where
you
you wanna plant this one? That's, yes, that's right. You put
then
this,
we-
okay?
1600. Okay. Can I drive it? Okay. So here I'm not sure this one. First one I'm coming, but a few things I can try. So let's put this one 1600 and we have 1600. Okay. And there are majority of 1600. 3 of them are 1600. That's one. Now what we do, we need to change this.
Have you?
We just bring it.
Yeah.
I'm not sure it's gonna work or not. Before you have 40, now let's make it 80. That way, we have 1800.
This work. Okay, so we can make it, or you can make it like you like transform. That's the problem. This one, that's one, you need. I didn't have to.
Excellent, maybe to change the name, to try that. So let's do it again.
So you know.
Will you also read the first one?
You have an M1, so that's where.
Let's make this one
And then you're supposed to have.
1600.
You, it's the same. That looks the same.
1600.
It's.
Where it isn't realizing.
So what happens is, at realizing it's not gonna look like the actual system. So you can do that one.
Yeah, they different. Now I figured out what is happening. So let's do this one.
So.
We need to change the name.
Because I think, yeah, you haven't, you don't have.
Let's say, let's put
So real ones,
this
that
one.
you're gonna look, they're gonna have the same value.
section 1600.
Capital and what would be there in capital pen.
Yeah, change the name or something.
So if you sub that, yeah, so it can.
Because you want 1600, right? And 200,000, so that will do. Change the name, area is changed. Now this one would be 1800. Let's put second one here, 18. This one,
Okay, so you know what to give them.
1800. And
What was
then
your,
1800. So
because like what I'm thinking.
you change it?
Like that will be the.
No, it will stay. So you need to change the section name or these two names. And that will do the job. And then when you come back here, and if you find, let's say this is similar, I'm not sure how to recall.
12 plus 9.
So yeah, here, if you got this 3 button, then you just click on 1600, then it will go to 1600. So if you click here, that is 1600. If you click here, that is 1600. If you click on here, that is 1800. You make sense?
Yeah, and then, after that, how do I find the placement? Do I do it in
In your static analysis, and then you go, and then you have displacements. And if you have a text report, you know, that will show the displacement, and then in the output, it will show you the text report. You don't know what do you mean by text report? You have not done it.
Second one, I don't everything right, and then.
I think in the very first week we done it, but I think I can show you if you run the analysis, then I will show you. And you have 2 ways to show. And I think in my email, when I send all the students, you see my text report there. Have you checked that?
Same sort of stuff.
On the LMS? There's some students saying that, okay, how to write the comments. So I have put the examples. In that one, I have put the reports. Yeah, but if you run it and then call me, we will check it, the displacements, okay?
What is that the first one?
It's
It's not that, if you increase the value, there's the other one.
All right, let me fix up and close this one. Yes, please, just give me a minute because they are not relevant to this workshop. So let me close. Thanks for the students online joining this one. We are finishing workshop here. Thank you. Stop recording.